sparser and sparser, and they start to fit out and sound ever more bizarre. And then, ultimately, beyond that point, there's a point where things drizzle out and stop altogether. And we can't say precisely when that happens or where it happens, but happen it will because of the limited nature of the world in which we live in. It's just a consequence of facing the reality that the physicists, the astronomers, the cosmologists are telling us that we inhabit. So in fact, I claim that to be very precise, there are no primes bigger than, say, 10 triangle 10 plus 23. There are no primes bigger than this one. It's not just that there are bigger primes, but we can't find them. No, I assert that it's actually the case that there are no primes bigger than this thing. There are just no numbers that can be expressible in our universe which have the property that they are bigger than this and are also prime. This is a very statement, of course. And you may say, well, it's just a matter of time before our computers get big enough and we'll be able to explore these regions and find primes. No. Okay, you're not going to find a prime bigger than this. Future viewers, am I right? With your viewers from 1,000 years from now. I'm willing to bet that you have not found any primes bigger than this number. There probably is more evidence to you that I'm right. There are no big primes of this kind. So, what about Euclid's proof? So Euclid's proof asserts that no matter how many finite primes you have, you can always find a bigger one. Well, it turns out we'll have to have a look at this, that Euclid's proof contains a subtle logical error. It's not a correct proof, in fact. Okay? If we look closely at it, not just kind of quickly look at it, but actually look very carefully at what the proof is telling us and what it's telling us to do, we see that there's some subtle assumptions built in that, upon closer examination, aren't supportable. So the proof is not in fact correct. The proof is correct for smaller numbers, yes, I'll buy that, but eventually the proof reaches a stage, some bounds where the arguments no longer apply, and the proof breaks down, and in fact the theorem is no longer a theorem, it's just plainly false. There are no prime numbers bigger than 10 triangle 10 plus 23. But it's not just results that go back to Euclid which are problematic. Many modern so-called theorems in number theory are simply incorrect as currently stated. They are simply not true. And they rely on a false understanding of the nature of the natural numbers. There really is a serious misconception floating around that basically pervades all of modern number theory. So almost all of these fancy modern theorems are in fact limited in extent. And they need to be recast in a more limited, careful way. The bounds of possible applicability of these theorems needs to be investigated. Are fraught with difficulty. So another serious problem is induction, where we try to prove things by this process of starting with one and then proving things one at a time. So this whole enterprise becomes problematic if we can't actually get to the number that we're interested in, say like 10 again, by counting from 1 to Z, one step at a time. Really, if your proof that something is true for Z involves starting with 1 and then proceeding one step at a time, from 1 to 2, from 2 to 3, from 3 to 4, and then keep going until you finally get to Z. That's your proof technique. And then you find out that, in fact, wait a minute, most of the numbers that we encounter between 1 and Z are, in fact, not actually reachable. We can't actually get to them because they're so vast not fitted the universe. Then that clearly breaks down the logical argument, right? That we no longer have proven our fact for Z. We've proven it only to the extent that we've been able to go from 1 to whatever number we're considering, one step at a time. It's a logical necessity. If you're only going to go one step at a time, you can only make statements about things that you can get to by going one step at a time. So we need to reconsider a lot of things in number theory. We need to think much more carefully and clearly. We need to take into consideration the real dichotomy between small, comfortable, familiar arithmetic and this much more problematic, almost inaccessible arithmetic that we eventually get to when we start to explore far outside our comfort zone. And one way to start to try to make things more precise and to nail things down more clearly is to go back to the very fundamental questions that we started with this video with, which is, what is exactly a natural number? It's sort of at the heart of the matter. What is a natural number? Well, we've met at least 3 kind of tiers, identifiably different ways of looking at natural numbers. So our first tier is really the one that we started this series with, where we were thinking about natural numbers in a very primitive fashion, basically as a sequence of strokes or marks on a page. And that's sufficient for us to define arithmetic, multiplication, and multiplication in a relatively simple kind of naive way, where we in fact don't actually even need to have names for such things. We can say this is mark times mark equals mark. And a little bit of a departure from what I did in that very first video is that now I'm putting these collections of strokes and marks in a boxes, because we're familiar with multi-sets. We're using multi-set kind of idea here. This is a multi-set of marks. Okay, that sort of makes it a little bit tighter. And of course we can then sort of recast this in terms of our familiar Hindu-Arabic formulation. This is really 7 plus 4 equals 11. This is really 3 times 4 equals 12. But then we can sort of represent this as just being a shorthand for this. So this kind of statement, from this point of view, is just a replacement or a convenient notation for expressing this more fundamental manifestation of the arithmetic of natural numbers. So with this view, a natural number is really well, it's a bunch of strokes and marked on a page, perhaps enclosed in some kind of box or container or multi-set. And then another big step up is to go to the Hindu-Arabic natural number presentation that we're familiar with, that we actually use in everyday life, where numbers now are things like 34 or 152. And the arithmetic is done at this level that we learned in primary school. 34 plus 152 is 186, 57 times 14 is 798, and so on. And although there's a natural connection between these two things, there's also a natural separation. And there's some senses in which this is a more sophisticated and more wide-ranging approach to numbers than this one. And then another big step is to consider just arithmetical expressions. So, for example, we could say, look at this number here, 3 to the 5th minus 14 squared. And that's an arithmetical expression for a number. And here's another arithmetical expression, 6 factorial. And here's another arithmetical expression, 13 times 59. Okay, so here we're working with some kind of arithmetical expressions, and we can do arithmetic with these arithmetical expressions as evidenced here. But you can see that this is going to be much more challenging to set up because we have to decide, well, what kinds of expressions we're going to allow, what are the rules that we're going to adopt, when are we going to decide when two expressions are equal, and so on. So, although we could, and perhaps we'll talk about this, it might be useful for us to really separate what we currently have. So currently we jumble all these together and say, oh, consider this number here, that's 4, and consider this number 798, and consider this number 13 times 59. We treat them all as more or less just different manifestations of the same thing. But what I'm saying here is that what we've been talking about really leads us to want to separate things into different levels so that there are different kinds of natural numbers. And we might actually introduce different types for what currently is just only one type. So we could say reserve nat to be a primitive natural number of this kind. And we could use num to represent a Hindu-Arabic natural number. And we could introduce something like num expression or numx to denote some kind of arithmetical expression. Although you have to be more precise about the nature of this kind of object. So this way we would have different levels of natural numbers and not just the single all-embracing container that we currently have. So let's say a little bit about that first type, the primitive natural numbers. So note that we're going to use MSET or multisets as containers for NAT. So that we really are adopting this data structure point of view here. And this is another example of the very useful application of multisets. That they give us a vehicle for introducing and creating, in fact, the natural numbers. Okay, so this is very different from the set theoretical formulation, as we described a few videos ago, attributing it to John von Neumann. You can see that a natural number is a set of sets, and everything is built up from the empty set. So there's sets and empty sets and other sets and so on, so it's nested inside each other in a rather complicated way. So here the possibility is that we can simplify things dramatically because if we use the MSET notation, then we only have these single primitive objects, which we might call a stroke or a mark, which then going to populate our MSETs and going to create our natural numbers for us. So here is a definition. Okay. A definition of what a natural number is. Actually, more precisely, what a primitive natural number is, if we want to be a little bit more specific. So a primitive natural number is an MSET of marks. This is what we call a mark. An MSET of marks is a natural number, and this type, nat, is going to be now our type that represents a primitive natural number. So an MSET of marks is specified by writing it down clearly and completely. There's now only one way of really officially writing down a primitive natural number, which is to write it out like this. It's an MSET of marks, so you have to make all the marks, and you put them in a square bracket box, and that is a natural number. That more precisely is a primitive natural number, an element of that. So note that this is similar, but somewhat different from our very first lecture, NF1. In that lecture, we hadn't talked about data structures. We didn't have the idea of sets or lists or ordered sets or multi-sets. And we didn't put our strings of marks or strokes in a box or container. But now that we are familiar with multi-sets and we're a little bit comfortable with them and we recognize that they're flexible objects, we are going to do that. So we're going to shift gears just a little bit. We're allowed to do that. And we're going to now regard natural number as a MSET of marks in the usual MSET notation. So MSETs, of course, I remind you, allow repetition. Definitely need that because there's only one type of thing that's happening here. And there's no commas because the order doesn't matter. You can interchange the order and it doesn't matter. It doesn't change things. Okay, so this is really a fundamentally new. Okay, so here departing from that, so our basic object is this stroke or mark, which is not to be identified as the number 1, which is rather this. So the number 1 is the MSET consisting of a single mark. Here I've written it again. Okay, so this mark here is not the number 1. The number 1 is now the MSET consisting of that single mark. That's the number 1. So this is a departure from what we did before, utilizing our familiarity with M sets. There's some clear advantages in making our natural numbers as multi-sets of these strokes or marks. So in particular, the boundaries are clear, so there's less ambiguity or possible confusion when we have lots of different natural numbers on the same page or on the same line. If we don't have the boundaries, then there's more likelihood that these things will run together, especially if we're wanting to juxtapose them or get them close to each other. So in particular, if we're multiplying M sets, say like this, then it's completely clear what we're doing, and we can get rid of the multiplication sign and just juxtapose the two M sets. So that's now possible. But if you didn't have M sets there, then this would be a rather dangerous thing to do, because it'd be easy to confuse this one with what we call 7. And there's another interesting consequence of working with M sets, because we've seen from our experience that in the world of M sets, there is a distinguished M set, which is the empty M set. Okay, so this empty M set, which we denote like this, is both natural and useful. And so if we're going to define a primitive natural number as an M set of marks, then it follows that we should allow the possibility of having an empty M set of marks. And so that means that what we usually thinking of as 0 naturally plays a role here. It naturally arises as a type of natural number, which is of course different from the historical story. It's also different from what we did in the first part of this series. We have up until now not treated 0 as a natural number, but now we see that when we make the shift to this data structure point of view, regard natural numbers as M sets of these more fundamental marks or strokes, then it's natural to allow 0 in the picture, and so 0 becomes a natural number. So this is a shift that we're making. And I don't apologize for it. I think we're open to the possibility of changing our minds. It's very important to have this ability and this willingness to change our minds. Let's do things a little bit differently from the way we thought we were going to do things before. Right? This is mathematics. It's not set in stone. We can proceed, erase something, change things, reconsider, look at things a few years later and say, actually, we should have done this, this, and this. And we need to be prepared to then go back and actually do things the better way, to rub out what we've got and to write in a new and better way. That, of course, applies to a lot of modern mathematics. And of course, the computer scientists can now rejoice, because now 0 is part of the natural number system, which computer scientists enjoy, because that's starting to count from 0. So this is very exciting. So we've harnessed our understanding of data structures for something very concrete and actually fundamental. Namely, we are pinning arithmetic onto the multi-set framework. We are creating natural numbers from a relatively simple kind of ingredient, and with this very important data structure kind of thing in mind of a multi-set. In our next video, we want to do something that's even more fundamental. We want to go down right to the bottom of the core of mathematics. So the natural numbers are pretty close to being at the core of mathematics, but I claim that there's really something underneath the natural numbers. That's sort of implicit in what we've been talking about here, but I want to really identify what it is. So there's a fundamental dichotomy in mathematics, a kind of a yin-yang, which hasn't properly been identified. We need to put our fingers very clearly on this and really identify this fundamental dichotomy, which is at the core of mathematics, and that we are going to use to build up our arithmetic in a, I think, a beautiful way. So in our next video, it's going to be a rather important one, in the sense that we're going to really introduce a almost philosophically novel way of thinking about what mathematics ultimately is really about. Once we get right to the bottom, what's the essence of mathematics? We're going to find out next time. I hope you'll join me for that. I'm Noah Wapner. Thanks for listening. Really far out in this remarkable successor limit hierarchy that we outlined in our last few videos. So basically what we're doing is we're creating bigger and bigger arithmetic by thinking about a sequence of operations, extending addition and then multiplication and then exponentiation, and then this triangle operation that we've used quite a lot, the square operation and so on. We want to extend this list of operations in a rather interesting way. Basically relying on two ingredients, the idea of the successor of an operation and the idea of having a limit of a given sequence of operations. So if we have a suitable sequence of operators or operations, say cross 1, cross 2, cross 3, then we can concoct this limiting sequence. So with these two different ways of extending further, we want to now explore the possibilities. And one kind of underlying question here is, how do we actually get our heads around what precisely a suitable sequence is? There's a bit of an open-ended aspect here that we want to explore, so we're going to try to pin things down, but I'm not going to pretend that I have a fully-blown, completely laid-out theory here. If I will, yeah, interesting aspects of this whole story is that it may not be possible to lay out from the beginning what we're going to do. It may be more like you proceed in a certain direction, and then once you get to a certain level, you have to start making new decisions. And the new decisions that you have to make aren't initially apparent from where you began with. So it's kind of a zigzagging really requires you to think in a novel way, continuously or sequentially as you proceed. All right, so I do hope that you had a look at the previous videos, because if you haven't, this isn't going to make a lot of sense. So make sure you watch the last few videos. And there we've created some kind of hierarchy, starting with these relatively simple operations that we're familiar with, and then proceeding on. Okay, so we start with the operation of addition, and then these first star operations of multiplication, exponentiation, and the triangle operation. Star 1, star 2, star 3. And that's generated our first limit operation, which we call star infinity, and then we shortly change the name to star n. Then we take the successor of star n to get star n plus 1, the successor star n plus 2, the successor star n plus 3, and then here we have a new couple of successors, and we can take the limit of the sequence that's starting with these to create star 2n. And we can take more successors, create star 3n, and then we have a situation where we have a new kind of pattern formed by this first limit operation star n, the second limit operation star 2n, the third limit operation star 3n, and that forms then a new sequence which has a new kind of limit which we'll call star n squared, which has then a successor star n squared plus 1, another successor, and then these three then generate a new limiting sequence, much as these ones did, called star n squared plus n. Okay, so we can keep going in a certain way, but at this point we want to become a little bit more efficient. So we want to, first of all, dispense with actually writing down the stars all the time. It's really only the subscripts that matter. So we can rewrite this thing without any stars, just the subscripts. So 0, 1, 2, 3, and then n, then plus 1, n plus 2, n plus 3, then 2n, 2n plus 1, 2n plus 2, 2n plus 3, 3n, and then jump to n squared. And then n squared plus 1, n squared plus 2, n squared plus 3, and that limit n squared plus n. Okay, this is described in the Mathematics 181 on the fourth slide there you see a really big picture. Okay, so now to be a little more efficient and also descriptive about what's going on, so to understand more deeply what is involved here, we're going to make some more simplifications. We're going to start to replace these successors with just dots. After all, it's very predictable. Once you have star n squared, then the next one is going to be the successor, which will just obtain by adding the 1 to the label. So for n squared, we know the successor is n squared plus 1, and the successor of that is n squared plus 2, and the successor of that is n squared plus 3. So we can have a short form by replacing the successors just with dots. So we can start with 0, which represents addition, and then this little dot here could represent the successor of 0, which is multiplication. The next dot, the successor of multiplication, which is exponentiation. The next dot, which is the triangle operation. And then these three dots generate the sequence whose first limit is n. So what we're going to do is kind of disregard or suppress the successors themselves, because they're sort of simple. And so we're going to sort of focus on the first limits that we see. So there's a limit n, and there's a limit 2n, and then 3n, and n squared, and so on. And something else that we're going to do is we're going to record the level of the limits. So this kind of limit here of n squared was different from the other kinds of limits because it was a limit of limits. It's a kind of level 2 limit. And so we might record that by putting a 2 under the arrow. So implicitly, these ordinary arrows should have 1s underneath them. Corresponding fact, these are level 1 limits. And this thing is a level 2 limit, so it gets a red 2 underneath it. Okay, so with these conventions, we can now have another look at this successor limit hierarchy, at least up to how far we've gotten so far, and see if perhaps in a slightly new light. All right, so have a look at this. This is our successor limit hierarchy, at least up to a certain point, and where we've been very efficient in just having successors represented by single dots. Okay, so let's have a look at that. Shows how things go. So we start with 0, and then our first limit is n. The next limit is 2n, next limit is 3n. These are all level 1 limits. And in these three level 1 limits, generate a new sequence which gives us a level 2 limit, n squared. Then we have some more level 1 limits, and they generate then another level 2 limit. Then another level 1 limit, 2 of them. These three then generate another level 2 limit. And now we're in a situation of having 3 level 2 limits. They themselves form now a new identifiable sequence. And we can take their limit. So the limit of n squared, 2n squared, and 3n squared is n times n squared, or n cubed. And that's a level 3 limit because it's the limit of 3 level 2s. And now we have something that goes off again because we now have a sequence with a 1 level limit, a 2 level limit, and then our first 3 level limit. That generates a new kind of sequence which has a level n limit, namely n to the n. Okay, now we go back to the way things were. Very exciting, we get a level n limit, and now we're going to go back down to ordinary successors with a level 1 limit, another level 1 limit, n to the n plus 2n, and then next 2 level limit, n to the n plus n squared, what's the same as here. So what's going to happen here now is going to be sort of a repeat of what happened previously. After this level 2 one, then we get a level 1, another level 1, another level 1, and then another level 2, and eventually another level 2, and then these 3 level 2s generate a level 3, which is n to the n plus n cubed. That's a lot like this one. And then, well, then we have the same kind of situation as we had previously. We had the original level 1, and level 2, and level 3, and that gives us a level n, which is going to be 2 n to the n.